This is the title of my talk. And so basically I'm going to speak about Mars, Europa, and focus on water, what can be detected by radar, because as Hervé mentioned, I am a radar person. Okay, so Mars and Europe. So that's it. So basically this is my something I need to add. I am currently at the head of the observatory of the Versailles Saint-Quentin-en-Yvelines University. So Mars and Europa, what do they have in common? Not much. Terrestrial planet discovered since prehistory, since you can see it from with naked eyes, distance from the sun, diameter, orbital period around the sun, atmosphere, very thin, basically CO2, and surface temperature, cold, but not that cold. And then Europe, an icy moon, discovered more recently, but not that recently anyway. Distance from the sun much higher. Distance from Jupiter, close to Jupiter. Diameter, in diameter, it's basically more or less half Mars. Orbital period around Jupiter, a few days. Atmosphere extremely thin, basically more oxygen, and very, very cold surface temperature. So the purpose of my talk is to try and find connection between the two bodies. And well, it comes to habitability, habitable zone, and liquid water. So let's say that prerequisite for the emergence of life is more or less commonly admitted. Liquid water, because this is an excellent solvent. Organic molecule, because of rich carbon chemistry. Energy. All that put in a suitable, reasonably stable environment for evolution to take place. There might be slightly different definition, but I will stick to this. Habitable zone, this is a region where liquid water at the surface can be found under specific, often Earth-like condition. If you are too close to a star, the water would evaporate, and too far from it, it becomes water ice. So we are focusing on liquid water here. Lying in the surface habitable zone doesn't imply habitability at the surface. That's not enough. And more than that, outside this zone, bodies like icy moon could be habitable at depths, not at the surface, but at depths. Here I've got a classic sketch that shows in green the habitable zone. I put the planets here. Basically, Earth is in the middle. Mars and Venus are not far away, and obviously the other planets are very far away. Here you have got exoplanet, inside, outside, depending on their sun mass, star mass. And here you have got surface habitat, and here you have got potential deep habitat. Due to tidal heating, for example, that might warm up inside this body and make that liquid water could exist. So I'm going to focus on liquid water here. Let's start with Mars. We've got few missions in orbit. The two first are in orbit, and then the other one are roving at the surface. There have been more missions than that, but these are the ones I will show data from. There is obviously a water-rich path of Mars, and you have got obvious morphologic hint and traces of this past. Here we have got a network of runoff channel. Here you have got teardrop-shaped island with impact crater at the upstream end, and also lobate crater, which are signs of water in the subsurface. Here too, outflow channel. So basically, there's many traces of that show that Mars had once a lot of liquid water. Some obvious morphological traces are, if you look closely, you will see round eroded pebble here, the same we find on Earth in riverbed, but they are small, maybe some 1 centimeter in diameter. And the studies have showed that it's interesting because this kind of information allow us to understand the past aqueous processes at the site. So here again, an obvious morphological trace of running water for a significant amount of time. Here I point to mineralogical evidence of I put trace of past and present water on Mars. We are slightly moving from past to present. Why is that? Because this is a map of detection of hydrated mineral from orbits that have been collected by mostly two instruments, Omega on Mars Express and CRIS and Mars Reconnaissance Orbiter. So you see these dots show places where hydrated minerals have been seen from orbit, detected from orbit. So they are still here, so which means that there is still water at the surface. They just see the skin depth. But anyway, it's surface detection. Present day water of Mars, polar caps, south, north. We have got not only water ice, but significant part of it is water ice. There is also CO2 ice here. Very, very thin amount, small amount of water in the atmosphere. I already mentioned hydrated minerals that contain water and subsurface. So are we looking for liquid or ice subsurface? Certainly both of them, and but this is why we are heading to Europa. So a series of missions started with Voyager, Pioneer actually, but Voyager 1 and 2 provided detailed image revealing Europa's cracked ice surface that are still very interesting for us. Galileo then, that started to point to evidence of a subsurface ocean, and also chemistry. New Horizon, a few flyby on the way to Pluto. And Juno, interesting because he also did some interesting magnetic field data acquisition that point to a buried ocean. So, extremely smooth, icy surface. There is no doubt. There is water ice at the surface of Europa. Crack ridges crisscross the ice crest. The blue-white terrain indicate almost pure water ice. It's a very young surface. We see very, very little crater. One is the one that you can see here, zoomed in here, that shows very white ejectas that are identified as almost pure ice, fine-grained pure ice. So it's basically surface, icy, water ice, and very young. Okay, if we go deeper, trying to understand what is beneath this ice crust, we can look at these reddish color, straight lines that are I think everybody agrees that they are due to mineral rising from beneath the ice crust, possibly salt, magnesium sulfate, or even sulfuric acid. So, which means if they are coming from beneath, it means that probably there is a liquid water beneath the crust. So this is one interesting evidence. And if we look at the surface again, we see a region of disrupted terrain, surface ice crust broken and seem to be refrozen, very, very similar to what we can find on Earth in places where the ocean froze, and which points to an active activity beneath the surface. So it looks like it could be an icy crust floating over a liquid layer. again, potential subsurface ocean. Maybe less obvious proof, but which is very interesting, is the magnetic field. Magnetic field measurement have been performed, and you see one simulation here. But basically what we have seen is that there is a magnetic field induced by the variation, temporal variation of the magnetic field, Jupiter's magnetic field induced in Europa. We have, I don't know whether, not sure you can see very clearly, but you have got kind of shape which has the line of the magnetic field that rotates. One are green, ones are green, and the other are bluish, and they don't rotate at the same with the same period. So basically, what has been observed is a field variation on Europa at a time scale of 11 hours, which correspond exactly to the Jupiter's rotation period. So there is this induced field. The other one is much longer. It's 84 hours. It corresponds to the orbit, Europa orbit around Jupiter. And this is a variation distance from Jupiter to Europa that produce this magnetic field. So basically, Europa doesn't see always the same magnetic field coming from Jupiter for different reasons, and the reaction is a creation in a conductive layer of current, electrical current, that would induce its induced magnetic field. This is what has been measured. So basically, the observation calls for an inductive magnetic field by Europa that requires absolutely conductive layer beneath the surface. The ice is not conductive. We need something conductive, and obviously comes to mind this is water, but salted water, because pure water wouldn't work. So this is a very strong evidence for a global salt water beneath the ice crust. Okay, so basically both Mars and Europe have something in common. They have serious potential for harboring life. So on Mars, there is evidence of past liquid water, and some region may still have underground water, frozen or liquid, still unclear, and we think that primitive life could have existed in the past within this liquid water environment. At Europa, it's more in the present that we think about potential life. There is there are so many hints that there is a vast subsurface ocean beneath the icy shell, and it really makes the best candidate for extraterrestrial microbial life. So these two bodies are very different for different reasons. We are very interested in looking deeper to confirm what is written here, because so far there is no proof, because everything is indirect. So these two bodies, it calls for a study of the subsurface, because the question we still have, possibly the answer are to be found in the subsurface. So, okay, subsurface exploration and radar. I'm biased, you understand, the MPI of radar. So, okay. So, but to be honest, we can do try and study subsurface, but different way. I just put three, but drilling. Yes, obviously. Drilling is operated from the surface. You cannot drill from orbit, obviously. The depth is limited, and it's destructive, obviously. Seismometer is very interesting, non-destructive method, but needs to be lying down at the surface, so it needs to be operated from the surface. Radar, the nice thing is that it can be operated from orbit, Marcy's charade, I will show you example, and also from surface. We are rovers that carries a ground-penetrating radar now, and it's a non-destructive method. So my favorite is the last one, obviously. Okay, just to make sure you understand, if you look at thermal and near-infrared spectral, the subsurface they have access to is microns. Thermal inertia, it's few centimeters, let's say. Gamma ray sensing depth is more the order of magnitude 1 meter. If you go to radar, it can go from 1 meter to kilometer, tenths of kilometer, hopefully. And seismometers, they go much, much deeper. They will be able to characterize the whole body down to the center of the body. So, electric sounding techniques. Radar is not the only one, but I will just mention the other one, but speak for radar. So, the electromagnetic wave can propagate through matter, which is not surprising, but also in vacuum, which is great. It's something that needs to be noticed, and this is why the reason why we can get information from Voyager. They travel closer you are from vacuum, the easier the propagation is. But here we are not speaking about propagation vacuum, but anyway, these have an opportunity share with seismometer to pierce through the surface and reveal buried structure. The information is obtained in non-destructive way, and the information is related to the electromagnetic property of the subsurface component you have in the subsurface. So basically, with a radar, with any kind of electromagnetic sounding technique, what you can detect is change, contrast in permittivity values. This is what it is sensitive to. It's not going to tell you anything about color, about... but indirectly, the permittivity value I would just mention is depending on physical parameter everybody could be interested in. So, a sounding radar, operation is simple. You have got an antenna, you transmit a wave, generally looking downwards. It propagates, reflect, interact, and in the end you have reception of the electromagnetic wave with the receiving antenna. That can be the same of the transmitting, can have two different and just the same. What you measure is a round-trip propagation time, so this is a propagation delay, and associated amplitude of different echoes. And with that you can build 2 or 3D of reflection, reflective intensity, and also if you process your data, you can produce 2 or 3D map of the estimated permittivity values. We have got also permittivity probe, but basically they have got electrode, and transmit a current between two electrodes, and you measure an electrical potential difference. You estimate an impedance value, and you get a local permittivity value just beneath your permittivity probe. And there are also transient electromagnetic. You create with a loop that needs to be lie down at the surface. You create a magnetic field, transient, using a loop, and then you get a vertical profile of conductivity value just beneath your loop. All this method needs, of course, hardware, but the interesting thing, the deeper you want to go, the larger the antenna, the loop, or the distance between the electrons must be. So basically, if you have got a small or tiny, you have got 2 electrodes here, you will go 20 centimeters deep. If you want to go 1 meter deep, basically it's more or less the same order of magnitude. You need to separate them. The same for the loop. If you want to go 100 meters deep, you need 1 loop, which is more or less 100 meters in diameter, which is complicated. For radar, the same. If you want to go deep, you have got large antennas, which is a problem. So I will be just focusing on radar and try to tell you the basic for radar. I mentioned geoelectrical property of material, so vacuum, you have got permittivity of vacuum, permeability of vacuum. Okay, this is vacuum, this is a reference because most of the time we speak about relative permittivity, epsilon r for relative and mu r for permeability. You see here that the okay, the permittivity value is complex. You have a real part and an imaginary part. This is very important to keep in mind because this has a strong impact. This value depend, both permittivity and permeability depend on composition, including porosity, vacuum being one element. So porosity, composition, temperature, and frequency. You know the frequency you use. You can measure temperature. So basically you have got a value that says, okay, I don't know exactly the composition, but I can constrain the porosity, for example. For non-magnetic media, of course, permeability is equal to 1. And for lossy material, say lossy or conductive material, the imaginary part is non-zero, and it results in a strong, potentially strong attenuation of the wave. Oh, here are a few equations, but then I stop here. So they are very simple. The wave propagation is driven by the permittivity value. Okay, the velocity, everybody knows that, the velocity of the wave is the one in the vacuum divided by square root of the permittivity value of the medium. When you have got smooth interface, very simple configuration, smooth interface, no antenna, the wave come very far away and straight, and everything is simple. Basically, you have got refraction. You know that here is the incoming wave, and this is a transiting one, and you know there is a change in direction. This is refraction. And what is interesting also is the amplitude of the reflective wave. That depends. It depends on what? Both depend on the ratio between the square of the permittivity value of medium 1 and medium 2. You have got the same for the amplitude of the reflected wave, and if you are a normal incidence, looking really downwards, the angle are null. So basically, it's boiled down to that. What is, but this is simple physics, maybe. Yes. And what is important here is that when you have a lossy medium, then you have attenuation in the material, by the material, which is exponential. It goes like that. Here you have got what we call penetration skin depth of penetration depth. D is a travel distance, F is a frequency, and okay. What is important to keep in mind is the penetration depth, so basically to what extent you can sound, increase when the frequency is lower. So if you want to go deep, you need to use low frequency, huge antenna. The penetration depth increase when the electric losses goes down. If your medium is not conductive, you will go, it's not, you can do anything to change it, but you will be able to sound deep. Okay? This is for very simple configuration. When the configuration is more complicated, here, for example, these are experimental data, wisdom data, sorry about that, it's just because I've got the data. These are ice wedge in polygonal terrain. So these are experimental data. If you want to compare it to simulated data, to try and interpret quantitatively what's happened here, you need to do a simulation. And here it's just a simulation that has been run from one location of the radar. And this has been done for 25 meters, so basically more than about 250 points. So you have to simulate for each location of the antenna here how it behaves with this ice wedge. You can see, and I'm not going to go into detail, but this is complicated. You cannot do this by just using Snell equation and Fresnel coefficient. So the simulation is very important because it is used to confirm interpretation, or yes, to choose between, you have got two interpretation, you simulate and you go, maybe you might be able to understand exactly what's going on. But to do that, you need to have simulation that takes into account the whole instrument characteristic, the antenna, receiving, transmitting, the radar waveform, the wavelengths, and you also need to be able to simulate very complex subsurface. Here you have got heterogeneous, you have got shape, the ice wedge is a bit simple, but anyway. So this was just to show you that this is an important part of data interpretation. Typical permittivity value. Okay, vacuum 1 and 0, no loss, and relative to vacuums it's 1. And here you see I find it interesting, but anyway. Liquid water is very high permittivity value, the real part is high, and the imaginary part can be high, can be rather low, but depending on how pure the liquid water is. If you go to seawater, for example, the real part is very strong, the same as here, but you have got a huge imaginary part, which means you don't penetrate. Electromagnetic wave don't penetrate in salty water. This is important because if we think that the water beneath Europa crust is salted, you will see very strongly the top, but it would be extremely difficult to sound down to see till where there is water. And the very interesting thing about water is that when the water freezes, you see the permittivity drop. Instead of 81, it's around 3, and you have got a small imaginary part, which means that when you have got, just figure out, you have got a swimming pool. During summer, what happened? You have got a strong reflection at the surface, and you don't see the bottom with your radar. If it falls down completely, you have got a weak reflection at the surface because you come from 1 to 3. The little contrast between the air and the ice, but you go through the ice with no problem, have got a strong reflection when you reach concrete or whatever it is beneath. So this is very intriguing because it totally changed. So when I say radar, when we speak about radar characteristic and capacity, it depends very much if the water is liquid or not. And to point to that, for example, dry sand, you have got permittivity between 4 and 6, okay, very low imaginary part, so almost no attenuation. But when the sand is wet, interaction with liquid water makes it conductive, and you don't penetrate. And if you look at clays, it's even worse. Wet clays are behaving more or less like seawater. So it's complicated. Okay, so basically, radar can penetrate deep into subsurface of icy body because the ice is favorable to penetration, provided your frequency is rather low. So we are speaking about megahertz. But liquid water strongly reflects the radar wave and prevent penetration. Okay, so I'm not going through that, but these are the list of sounding radar designed for solar system exploration. I started by the first line, Earth-based radar observation that were performed from Earth, but okay, you see the date. And then all these are supposed to fly one day, and you see Mars in bold, Mars, and Europa, and you see that for Europa you have got 2 missions with 2 radar. One is here, RIME, and the other one is Reason. And for let's say Mars, we have got Marsis and Charade in orbit, and currently RIMFAX, which is operating from the surface, accommodated on a rover. Okay, so here these dots represent all the the radar of the previous table, and you plot. You have got horizontal, it's the date, the year, and here on the vertical axis you have got the center frequency. So remember that the lower the frequency, the deeper we go. So basically what is going low, here we have got Marcy's charade, here you have got icy moon, here we have got Venus, next mission to meet Venus, and here with this kind of diamond marker, we have got the GPR carried accommodated on rover operating from the surface. They cannot carry on a rover very long antenna, so they need to have high frequency, and they're here. So basically, penetration increase when the frequency goes down, but the vertical resolution is it is the opposite. It gets better when the frequency bandwidth get larger. But so here you have got the bandwidth, and you see that there is a trend that going to large frequency bandwidth to get a better vertical resolution. The problem we have is that the central frequency of the radar will limit the frequency bandwidth we can have. If you have high frequency, you can be large around this high frequency. If the frequency is low, you cannot be large because there is zero limit. So there is an important trade-off, very complex one, tricky, to be made according to the science objective. Okay, either you want to go deep, but you know that your resolution is not going to be as fine as you would like, or to go less deep, but focus on the resolution you want. So, illustration, what sounding radar are doing. This is the data from RIMFAX on Perseverance. So this is an illustration of how a radar can reveal the buried structure and then so understand the geological evolution of the site. Because when you go deep, you go in the past and you understand what comes first. So basically, this is the area that has been sounded by or traveled by the rover, starting by RIMFAX, and here is a zoom of this part here. You have got a 3D representation of the topography. Okay, and the question people were asking is, what is the oldest terrain? Is this one coming on the top of this, or is it the opposite? This was before had been filled by what we see on the floor. And the answer is given by RIMFAX data. RIMFAX data have been, added here. You see this line, and there is obviously a line that goes almost horizontal, that go deep in here because it goes. So obviously the answer is clear. This is the older terrain, and here we have got the younger terrain because it comes above it. Okay, and RIMFAX, for example, is able to penetrate from 10 to 50 meters, depending on the environment, of course, with a vertical resolution of 15 centimeters, more or less. So this is the kind of question a radar can answer to. This is my radar. I have a soft button. So with the ExoMars, the science objectives are very different. On ExoMars, there is a drill that is going to collect a sample at 2-meter depth that will be analyzed inside the rover body. So we don't want to drill blindly. We want to know where to drill, what is the best location, what is the safest location, and this is where wisdom is coming. So basically here, this is a field test in Svalbard. You have seen here is the antenna of wisdom. The electronic is somewhere here. This is a very small radar, 1 kilogram, 0.5, something like that. And this is some data that have been acquired on this terrain. So the interpretation is here. We have got the air. Homogeneous ice, we know that because we know the permittivity of ice. The permittivity we have been able to estimate is 3.2, so we know this is pure ice. Beneath the layered ice. And here, just here, this is a riverbed. So you see, the kind of information we can provide is totally different. You see the scale. Here we are speaking of, this is, 2 meters, not even. And we are moving around 10 meters. Okay? So, depending on what your objective is, you will have a local estimation, very resolved resolution, and or you want a big picture, go deep, and then you go with high frequency, low frequency. Frequency of wisdom make it vertical resolution is around 3 centimeter, penetration depth a few meters, depending on the material. So back to Mars. So this radar that in orbit that reveals the Martian polar caps. So Mars is on the Max Express, operating at 2 megahertz. This is very low frequency. Vertical resolution, you see, it's not better than 150 meters. Okay, it means that it's not able to distinguish, disentangle two interfaces which are less than 150 meters apart. Penetration depth is several kilometers. It penetrated in the ice about 4 kilometers, but we don't know. So this is a radargram along the polar cap. You see here surface, and here you see something very strong here. This is rocks, bedrock beneath the ice. We see that the ice is layered, but it's not very clearly resolved. So, charade, 10 times higher frequency, and you see the vertical resolution, 10 times better, penetration depth more or less 10 times better, worse. And what will charade see of that? That's it. Okay, so clearly something is missing. It doesn't see that. Why? Because it's not able to go that deep. But we clearly see that the surface is much finely described. And if we zoom in, it's the same data, but zoomed, we see very, very clear layer here. And we see also something very interesting here. This is CO2 ice. Something that Mars was unable to see because it's a detail for such a radar. But here it's very transparent, and CO2 ice is even more transparent than water ice. So you see, Mars was designed to try and find liquid water on Mars, and charade was designed to focus on slightly shallower. Not that shallow, but a shallower surface, and provide very interesting data set. Okay, so one result, I'm speaking about liquid water. So there is a paper published in 2018 by Europa et al. That say radar evidence of subglacial liquid water on Mars. So I'm going to tell you how it works. Detection of liquid water beneath the southern polar cap. So this is polar cap, south, and here we are focusing on this area. This is the investigated area. Okay, here you have got one radargram. You know now how it works. This is basically, you have got horizontal distance. This is the surface. Here you have got layered. So surface reflection, layered ice, and the basal reflection, the bedrock. What is interesting in the data set is most of the time the strongest reflection is seen at the surface. When you go deep, you have lost a lot of energy, and what arrives at the bottom after hundreds of meters is a weak signal, so it cannot reflect very strong. What is surprising here is that this reflection beneath the ice is stronger than the one at the surface. Okay, so this was very interesting. They say very intense deep reflection beneath the ice shell. So it means that beneath this ice shell there is something that provides a very strong contrast with ice. One possible, the easiest answer might be salted liquid water. And this is a story of this paper, and it says that I just show you one radiogram, but obviously Charad did several passes around the area, and you have here in blue strong signal coming from the, it's not surface, but from the bedrock, and faint signal in yellowish. So there is a place, this kind of triangle, where the reflection is very strong. This is interesting. They have been trying, doing kind of simple, using simple equation, more or less the equation I showed you before, because the configuration is easy. It's flat and it's far away, so they can assume that the wave is a plane wave. So basically, using Fresnel coefficient, slightly more sophisticated, but anyway, the physics is here. They have been estimating the permittivity value at this pattern, providing this strong reflection. And what they see is for this yellowish area, the permittivity value is around 6, 7, which is more or less consistent with rock, not yes, rock, let's say. And in this bluish area, blue area, you see that the permittivity value goes very high. And you have got strong permittivity values that are not consistent with rock. So they are consistent with salted water, this is clear. So this is what the author suggests, that the water is hypersaline for two reasons. It needs to be very with salt in order to be liquid, and also salt increase permittivity value. So for both reasons, it's important that this water is not pure water. So basically, this is a very interesting result. This is the only clear detection, something very reflective beneath the surface of Mars. And this has been published with this paper. Discussion. I'm not going to that, but I just copied and pasted a few discussions that have been published after the publication of this paper. So the three first say no concentration of salt is sufficient to melt ice at the base South Pole, blah, blah. The bright reflection could be caused by contrast in the electrical conductivity of material near the surface, which has not been considered in the paper. Laboratory measurement observation just outside the ice cap shows that reflection can be produced by a layer of smectite tip clays as little 1 or 2 meters thick. The last one says that they have been looking at topography anomalies, and they offer independent support of the presence of basalt water beneath the area. So the last one is supporting the previous paper. But you see there are 3 papers, but several papers saying, wow, this is not obvious. So this is indirect proof. This is the best we have so far, liquid water detected by radar on Mars. But people are still debating. Okay? So, something interesting. Independent evidence provided by the seismometer on InSight. So, the author says that the mid-crust composed of fractured igneous rock saturated with liquid water best explains the size data. Nothing to do with radar, it's seismometer, and they have a hint for liquid water filling the cracks and hole of the crust. But they said that the amount of groundwater stored this way, could cover the whole planet to a depth of 1 or 2 kilometers. So this is huge quantity. But it's not a reservoir, like the one Mars is, that would be a unit of water. It's kind of saturated the rocks. And this reservoir is likely to be located between 11 and 20 kilometers below the surface. I don't think there is any chance that a radar would be able to detect that because it's too deep, it's not in ice, so the propagation is attenuated and it's too complicated. I don't think we will ever be able to confirm that by radar. Okay, this is Mars. So as for Europa, there are two missions which have been launched. One is ESA, JUICE mission. The other one is NASA, Europa Clipper. So Europa Clipper is a NASA mission to Europa, as the name says. It has been launched last year. It's designed specifically to perform detailed reconnaissance of Europa ice shell and subsurface ocean and assessing its potential habitability. Okay, the objective, surface composition, to use imaging spectrometer to analyze surface material, identify salt and acid, confirm what we say about this reddish color element. Ice shell and ocean, this is the job of the radar. Use a radar sounding to probe the thickness of the ice shell and search for subsurface water. They don't say they are going to try and estimate the thickness of the ocean because penetration is going to be extremely limited. So radar can penetrate the ice, but it would stop at the bottom, at the top of the ocean. Geology and tectonics, to study surface feature to understand geological process and tectonic activity, atmosphere and plume, investigate tenuous atmosphere and potential water vapor plume. There is a hint for existence of water vapor plume that has been made based on the plasma measurement around Europa. Instrument, there is a bunch of instruments, 8 or 9. So why that? It's because you will see in the next slide, but when you want to try and understand something as complex as a planet or even a limited site, one single instrument is not going to give you the answer. So you need to have a strong synergy between instruments. On ExoMars, for example, there is a radar, there is a drill. In the drill, there is an infrared spectrometer that is going to drill, and we will cross-correlate the data. And you have got the image of the surface that needs to be consistent with what you say of the subsurface. So there is constant discussion between instrument interpretation of the data. This is a teamwork. Basically, there is this, and in the middle of them, there is reason, the radar sounding to probe the ice shell and ocean. Okay, so the reason instrument has been designed to test 3 hypotheses. Ice shell of Europa hosts lenses of liquid water and near surface brains. Okay. Beneath the ice shell, there is an ocean decoupled from the silicate interior. Not sure how they are going to handle this, the end of the sentence, but detection of the ocean is something that is obvious. Radar is done for that. And then the exosphere, near surface, ice shell and ocean participate in exchange, essential to the habitability of this moon. And here you have got artist view. What is interesting in this radar, it has got 2 frequencies, one lower at 9 megahertz, and the other one 60. The 60 is going to focus on shallow, the crust, and try and have access to small structure, layer, for example, while the other one is aiming at as deep as possible. Okay. And okay, so it operates at 2 frequency. Just said that. It's a very versatile radar because it operates as a radar, to detect crust or to characterize crust and potential ocean. This is a radar sounding normal job. And then it will study the topography of the surface because it will have an altimeter mode and composition roughness of the European surface, focusing on the surface. And it will also study the ionospheric activity because when you transmit with a simple antenna down, basically they're also signal going up, and you can sound the ionosphere with that. This is something that Mars was still able to do. Here you've got experimental data acquired at 60 megahertz, so the high frequency of reason in Antarctic from a plane. So you see the kind of result we get, surface, which is ice. You see basalt crevasse. This is rock. You see layer inside, surface crevasse. And but when you look at the depth, you see this is half kilometer. So you have got one kilometer of icy crust. You can see beneath. Okay, this is not salted water, not too salted water, and. Okay, nature, it seems that the signal vanish. I don't know how deep it could go, but difficult to think that it's going to go more than 10, up to 10 kilometers in. But this is a very nice data. So this is an illustration of the synergy between instrument of the payload. So basically, there are a lot of arrows that points to, for example, reason is contributing to temperature, to density, to thickness, to circulation. I added this one. I don't know why they didn't put it. It's a camera. Camera is obvious. It's obvious synergy with everybody. So, okay. And then I think that reason would contribute to composition, salinity, everything. So you have got some very important work, network between scientists, because it's very essential. I think this is the most interesting job is to discuss with other people just like you. Everybody has got a different background, and this is in a team that interpretation comes the best, according to me. So, JUICE, the ESA mission to icy moon. It's not a European mission, but it will do some flyby on Europa. It's aiming at studying Jupiter and its three largest moons, Ganymede, Callisto, and Europa. Launched 2 years ago. It should arrive at Jupiter in 31. Okay, objective, not a surprise. Characterization of the icy moon to understand their composition, structure, and potential habitability. Jupiter environment, examining Jupiter atmosphere, magnetosphere, interaction with the moon. Astrobiological potential, assess the moon's capacity to support life by studying the subsurface ocean and geological activity. So more or less the same science objective. Not a surprise, because there's the question everybody wants to get the answer to. Instrument, well, more or less you have got the same. And here's the radar, RIME, for radar for icy moon exploration. That is going to probe subsurface. You have got the plasma spectrometer, and you have got study plasma for magnetic field and stuff like that. So this is also a suite of instruments, a payload, very rich payload to make the best of this mission. So RIME is a radar sonder optimized for the penetration of the Galilean moon up to a depth of 9 kilometers, is what they say, with a vertical resolution of 30 meters in ice. It operates only at 9 megahertz. They don't have this high frequency for the shallow subsurface. And they are using 16-meter long antenna. Just noted that for more than 3 weeks they've made effort to try and deploy the antenna because they were kind of stuck. They managed to fix the problem, but it's always a stress just for When Mars was launched, they were very concerned by the deployment of the antenna. They didn't want to jeopardize the whole mission. So basically, they wait until the official mission, minimum mission, was completed to deploy Mars's antenna. That worked perfectly well. But because they knew that the boom were made of several parts and it would go. Simulation showed that it could go anywhere. So everything went fine, but they had to wait a long time, several months, to be deployed. Here, they didn't want to wait, but they had to wait because of some problem. So when you have got a radar to process the data and to obtain very I'm fixed. I have got this kind of feelings that we need to be as quantitative as possible with radar. And so it's essential that your instrument is fully characterized. When you have got a radar like Wisdom, which is small like that, you go in an anechoic chamber, it's okay. You do whatever you want. When you have got a radar that has the 30-meter long antenna, it's not that obvious. So basically, what has been done for RIME? Two different things. The first, maybe the easiest one to understand, is I've put the RIME antenna. This was done by Airbus beneath an helicopter, and they have performed a flight campaign. Okay, just holding it like that with an helicopter. For sure, it was not operating at hundreds of kilometers of the surface, but this is interesting. You don't have interaction with the structure. So this is experimental data. The other one is more complicated. It's a scale model. I think it's 1/16 of the real scale. So they scale the model of the radar, but also of the spacecraft. You see, it's this little model. They put it in an anechoic chamber and have been able to perform measurements. So to study the interaction between the antenna and the spacecraft body, which is something you need to characterize, because there is for sure, there are interactions. You get echoes that come from the spacecraft. You want to know them well enough, accurately enough, that you are able to remove them from your experimental data to make sure you focus on what is real. Okay, so this was. And I don't know what time, but this is my last slide. It's okay? Conclusion. So, sounding radar are extremely powerful instruments to look and characterize subsurface and surface from orbit or from surface. The choice of the center frequency and the bandwidth is driven by the instrument mission objective. This is something very important. You can choose. You cannot go deep with a fine resolution, this for sure. This is a trade-off, but when you design your instrument, you need to think about the objective. What is the objective? And then you do your best. But this is the choice. The interpretation are almost always difficult, unless you are in very, very simple environment, and they are done knowing information people would provide. If you know you are sitting on ice, okay, this is interesting. You know what is beneath. And then this is starting point. So you need to rely on accurate numerical electromagnetic simulation to confirm your hypothesis. This is very, very important. You need to perform experimental tests in well-documented environment. For example, the antenna that was carried by this helicopter. You are basically in vacuum. You know exactly where the ground is. This is well-documented environment, and you check that what you are expecting from your instrument you can get in this simple condition because you know them. You need also to have, or to have people perform for you lab measurement, allowing you to know the permittivity value or of relevant sample, analog sample. For example, I told you that pure ice is 3.2. We know that because some permittivity measurement in lab have been performed. Then you can put salted water, you can put ice with mixed with sulfate, I don't know. This is interesting because if you know what is there, because you have seen it from spectrometer, this is some information you can put in your model and not start from value which are absolutely... So what I feel is you cannot do radar if you don't have access in certain way to these three kind of information. And then you need to have process code to process the data, which is not always easy, but this is another part of the job. So, would like to emphasize the fact that water is a very wide material for radar. You know that liquid and solid is a totally different behavior. So ice is very friendly, while liquid water prevent penetration. This is why radar are really the perfect instrument to try and sound the icy crust. So this is why they did so well on Mars to sound the polar cap. This is a way we have been able to estimate the quantity of frozen water on Mars. It's because the radar said there is a 3.7 thickness of almost 4 kilometers of ice. That gives you an order of magnitude. So, of course, this is perfectly suited to detect buried reservoir of liquid water, provided that the depth is compatible with the penetration depth of the radar. I'm done.